Something appeared in our skies on July 1st, 2025, not from here, not from anywhere in our solar system. And as you settle in tonight, wherever you are in the world, I want to tell you about it. Leave a comment below telling me where you're watching from and what time it is there right now. Are you in New York at midnight, London at dawn, Tokyo in the afternoon? I'm curious. Before we begin, let me say this. There's no rush, no deadline. The story I'm about to tell you has been 4.5 billion years in the making, so a few hours of your time won't change anything. Forget about your clock. Forget about tomorrow's meetings. Just let go. Let the information wash over you. Some of you will drift off halfway through. Some will make it to the end. Both are perfectly fine. This object has a name. 3IATLAS. 3 simple syllables that represent something extraordinary. The third visitor from beyond our cosmic neighborhood, the third messenger from another star system, and unlike anything we expected. Now, you might be wondering what makes this particular chunk of ice and rock worth 100 facts. Fair question. After all, comets have been observed for thousands of years, but this one is different. This one doesn't belong here. This one came from somewhere else, traveling through the darkness of interstellar space for longer than human civilization has existed. And some people, including a rather famous Harvard professor, think it might not be a comet at all. So get comfortable, adjust your pillow, let your muscles relax, and let me tell you about the visitor that has astronomers around the world staying up late, pointing their telescopes at a single moving point of light, trying to understand what exactly is passing through our solar system. The first fact you should know is that 3IATLAS was discovered on July 1st, 2025, at exactly 5:15 Universal Time. The telescope that spotted it sits in Rio Hurtado, Chile, in the Atacama Desert, one of the driest places on Earth. The sky there is so dark, so clear, that you can see things most people never will. The asteroid terrestrial impact last alert system, known as ATLAS, wasn't looking for interstellar visitors. It was hunting for rocks that might hit Earth. Instead, it found something far more interesting. The discovery itself was almost accidental. The object was moving through one of the most difficult regions of the sky to search, directly in front of the galactic center. Imagine trying to spot a single firefly against a backdrop of 1 million stadium lights. That's what the ATLAS team accomplished. The dense star fields of Sagittarius, where the heart of the Milky Way blazes with ancient light, nearly hid this visitor from our view entirely. Within hours of the first observation, astronomers started checking old images. This is called precovery, the process of finding an object in photographs taken before anyone knew it existed. They found 3IATLAS in images from June 14th, 2025. It had been there all along, moving silently through our solar system, and no one had noticed. By July 2nd, just one day after the official discovery, telescopes around the world were turning their attention toward this single point of light, the Minor Planet Center, which catalogs every asteroid and comet, had already received reports from 31 different observatories. The speed at which the astronomical community mobilized was remarkable. Within 48 hours, over 122 observations had been logged. The naming convention tells its own story. The prefix 3I means this is the third interstellar object ever confirmed. The I stands for interstellar. The number 3 is sequential. Before this, we had only seen 2 others, Oumuamua in 2017 and 2I Borisov in 2019. In the entire history of astronomy, spanning thousands of years, we have confirmed exactly 3 visitors from beyond our solar system. Atlas is the survey that found it, so the object carries that name. But it also received the designation C2025N1, which is the standard naming system for comets. The C means it's a non-periodic comet, one that won't return. The 2025 is the year of discovery. The N indicates it was discovered in the first half of July. The The number 1 means it was the first such object discovered in that half-month period. When astronomers first calculated its trajectory, they found something definitive. The orbital eccentricity was 6.14. Now, that number might not mean much to you, but let me explain. An eccentricity of 0 would be a perfect circle. Earth's orbit has an eccentricity of about 0.017, nearly circular. Halley's Comet, which returns every 75 years, has an eccentricity of 0.967. Anything above 1.0 means the object is not bound to the sun. It will never return. It's just passing through. An eccentricity of 6.14 is extreme. It's the highest ever recorded for any object in our solar system. This wasn't even close to being ambiguous. The math was absolutely clear. This object came from interstellar space and would return to interstellar space. It was making a single loop around our sun and then leaving forever. The incoming velocity was measured at 137,000 miles per hour, or 221,000 kilometers per hour. That's fast by any standard. But when you're coming from interstellar space, it's actually relatively slow. The object was traveling at about 61 kilometers per second relative to the sun when discovered, a leisurely pace in cosmic terms. Observations revealed that the object was approaching from the general direction of Sagittarius. This is significant because Sagittarius is where the galactic center lies. The object was coming toward us from the direction of the Milky Way's core, from the direction of billions of stars clustered in that ancient, crowded region of our galaxy. The distance at discovery was approximately 670 million kilometers from the Sun, placing it roughly within Jupiter's orbital distance. For context, that's about 4.5 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. So when we first spotted it, 3IATLAS was already well into our solar system. The object was moving inward, heading toward the Sun. Its trajectory would bring it to perihelion, the closest point to the Sun, on October 30th, 2025. That date was calculated with extraordinary precision, October 30th at 11:44 Universal Time, plus or minus just 2 minutes. The predicted distance at perihelion would be 1.356 astronomical units, or about 202.8 million kilometers, placing it just inside the orbit of Mars. During its approach, 3ATLAS would never come closer to Earth than 1.8 astronomical units, roughly 270 million kilometers. To put that in perspective, that's farther than the distance between Earth and Mars at their closest approach. There was never any danger of collision. The object posed no threat to our planet. The closest approach to Mars would occur on October 3rd, 2025, when the visitor would pass within about 30 million kilometers of the red planet. This proximity created a rare opportunity. Multiple spacecraft orbiting Mars could potentially observe an interstellar object, something that had never been done before. The size of 3IATLAS was difficult to determine at first. When you're looking at something hundreds of millions of kilometers away, measuring its actual dimensions is challenging. Initial estimates based on brightness suggested the nucleus could be anywhere from 440 meters to 5.6 kilometers in diameter. That's a huge range of uncertainty. The brightness itself was puzzling. For an object at that distance to appear as bright as it did, it would need to be either very large or very reflective. If it were a rocky asteroid with a typical albedo of 0.05, meaning it reflects only 5% of the light hitting it, then it would need to be about 20 kilometers across. That would make it enormous, far larger than the previous interstellar visitors. However, if it were a comet surrounded by a cloud of dust and gas, then the brightness could come from the coma rather than the nucleus itself. The coma is the fuzzy envelope that forms around a comet's nucleus when ice begins to vaporize. A much smaller nucleus could produce the observed brightness if it was actively outgassing. Within days of discovery, multiple telescopes confirmed cometary activity. David Jewett and Jane Liu, using the Nordic Optical Telescope, reported that the object was clearly active with a diffuse appearance. The Instituto de Astrofísica de Canarias, using the 2-meter twin telescope at Teide Observatory, confirmed the same thing. This was definitely behaving like a comet. The color was notable. Multiple observations showed that the coma had a reddish tint, indicative of dust particles. This reddish color was similar to what had been observed in 2I Borisov, the previous interstellar comet. The red color suggests the presence of organic compounds, complex carbon-based molecules that form in cold environments. High-resolution images revealed the shape and size of the coma. Using the Gran Telescopio Canarias, one of the world's largest optical telescopes, astronomers measured the coma at approximately 26,400 by 24,700 kilometers in diameter. That's roughly twice the diameter of Earth. This enormous cloud of gas and dust was being ejected from a relatively tiny nucleus. The shape of the coma was slightly elliptical rather than perfectly round. This asymmetry suggested that the outgassing wasn't uniform across the nucleus. Some areas were more active than others, possibly due to variations in surface composition or the amount of sunlight hitting different regions as the nucleus rotated. NASA's Transiting Exoplanet Survey satellite, known as TESS, had actually observed 3 IATLAS before anyone knew it existed. Test data from May 7th to June 3rd, 2025, showed that the comet was already bright and active when it was roughly 6.4 astronomical units from the Sun. This was surprising because water ice doesn't typically sublimate at that distance. The Sun's heat isn't strong enough. This early activity suggested something important about the composition. If water ice wasn't responsible for the outgassing at that distance, then other volatile substances must have been vaporizing. These are called supervolatiles, ices that sublimate at much lower temperatures than water. Carbon monoxide and carbon dioxide are common supervolatiles in comets. The Hubble Space Telescope turned its gaze toward the visitor on July 21, 2025. The resulting image showed a teardrop-shaped cocoon of dust streaming away from the nucleus. Because Hubble was tracking the moving comet, the background stars appeared as streaks in the exposure, creating a beautiful contrast between the static universe and this moving visitor. Hubble's observations provided refined estimates of the nucleus size. By August 20th, astronomers could state with confidence that the upper limit on the nucleus diameter was 5.6 kilometers, though it could be as small as 440 meters. This was still a large range, but it was much better than the initial uncertainty. The James Webb Space Telescope, the most powerful space telescope ever built, observed 3 IATLAS on August 6, 2025, using its near-infrared spectrograph. Webb doesn't just take pictures. It splits light into its component wavelengths, creating a spectrum that acts like a chemical fingerprint. This was when things got really interesting. Webb detected the presence of water ice and carbon dioxide ice in the coma. These are common components in comets from our solar system, so finding them in an interstellar comet was expected. But the ratios were not normal. Not at all. The carbon dioxide to water ratio was extreme. Webb measured it at approximately 8:1. For every 1 water molecule, there were 8 carbon dioxide molecules. This ratio exceeded what would be expected for a comet at that distance from the Sun by more than 6 standard deviations. In statistical terms, that's enormously significant. Most comets from our solar system show substantial water vapor relative to carbon dioxide. Water is typically the dominant volatile in cometary comas, but 3 IATLAS was different. It was producing vast amounts of carbon dioxide while releasing comparatively little water. This chemical composition was highly unusual. NASA's SPHEREx mission, which observes in infrared wavelengths, corroborated Webb's findings. Between August 7th and August 15th, SPHEREx imaged a vast carbon dioxide coma extending at least 348,000 kilometers around the nucleus. Meanwhile, it failed to detect a comparable water cloud. The carbon dioxide was dominating the activity. There are 2 main theories to explain this unusual composition. The first suggests that 3 IATLAS formed in a unique environment, perhaps in a region of its parent star system that was particularly rich in carbon dioxide ice or unusually poor in water ice. Different locations in a planetary system can have different chemical compositions based on temperature and the availability of materials during formation. The second theory proposes that the nucleus has a protective surface layer. This crust might be suppressing water sublimation while allowing carbon dioxide to escape more easily. If the surface had been altered by radiation during the object's millions or billions of years traveling through interstellar space, it could have developed a thick, insulating layer that preferentially retains water ice beneath it. Spectroscopic observations using the Very Large Telescope in Chile detected additional molecules as the comet approached the Sun. Cyanogen, known by its chemical formula CN, was identified, so was nickel emission. These detections revealed that the chemistry of 3-IATLAS was complex and evolving as solar heating increased. The activity level was being measured continuously. By early August, the James Webb Space Telescope estimated that 3-IATLAS was losing approximately 150 kilograms of mass per second. That might sound like a lot, but for a massive comet, it's actually relatively modest. The gas was being expelled at a velocity of about 440 meters per second. Here's where things get truly fascinating. Between May and September 2025, over 4,000 astrometric measurements of 3-IATLAS were collected from 227 observatories around the world. Astrometric measurements track the precise position of an object in the sky. When you plot those positions over time, you can calculate the object's trajectory with incredible accuracy. Comets typically don't follow perfect gravitational paths. When ice vaporizes on the surface, it doesn't just turn into gas. It creates jets that act like tiny rocket engines. These jets push the comet, causing what's called non-gravitational acceleration. The comet's path deviates slightly from what pure gravity would predict. Researchers Avi Loeb, Richard Cloete, and Peter Veer analyzed all those astrometric measurements and found something remarkable. The non-gravitational acceleration of 3-IATLAS was less than 15 meters per day squared. That's an upper limit, meaning the actual acceleration could be even smaller, possibly even zero within measurement uncertainty. This finding was significant because it contradicted what should be happening. The object was clearly outgassing. Webb had measured the mass loss. There should have been a measurable push on the trajectory, but there wasn't, or at least not one that could be detected. The principle of momentum conservation provides the answer. If a comet is expelling gas but not showing measurable trajectory changes, then the nucleus must be extremely massive. The heavier the nucleus, the less it gets pushed by the same amount of outgassing. It's like the difference between firing a water pistol while sitting in a canoe versus while sitting in a cargo ship. Using the measured outgassing rate and the lack of detectable trajectory change, the researchers calculated a minimum mass for the nucleus. They determined it must be at least 33 billion tons. That's an enormous mass, far greater than the previous interstellar objects. A mass of 33 billion tons, combined with reasonable density assumptions for cometary material, suggests a nucleus diameter of at least 5 kilometers, possibly larger. Some estimates push it to 12 kilometers or more. This would make 3-IATLAS 3 to 5 orders of magnitude more massive than Oumuamua, the first interstellar visitor. This brings us to a statistical problem. Models of how planetary systems form and evolve predict that smaller objects should be far more common than larger ones. It's easier to eject small rocks and ice chunks than massive ones. For every 10-kilometer object ejected into interstellar space, there should be hundreds of thousands of smaller objects. Based on these models, astronomers should have detected hundreds of thousands of Oumuamua-sized objects before encountering something as large as 3-IATLAS. Yet here we are with exactly 3 confirmed interstellar objects, and the third one appears to be by far the largest. The probabilities don't add up. This is what some researchers call the 3IATLAS size anomaly. There are several possible explanations for this statistical puzzle. Perhaps our models of planetary system formation are incomplete. Perhaps large objects are ejected more easily than we think. Perhaps smaller objects are harder to detect than we believed. Or perhaps we've been extraordinarily lucky or unlucky, depending on how you look at it, to observe this particular visitor. The trajectory of 3IATLAS raised additional questions. When astronomers traced its path backward in time, integrating its motion through the gravitational influences of all the planets and the Sun, they could estimate where it came from. The calculations showed it likely originated from the thick disk of the Milky Way galaxy. Our galaxy has structure. There's a thin disk where most star formation happens, where young stars like our Sun reside. Then there's a thick disk, populated by older stars with lower metallicity. These older stars formed billions of years ago when the galaxy was younger and had fewer heavy elements. By analyzing how far 3IATLAS strays from the galactic plane as its trajectory is integrated backward, researchers estimated its age. The object appears to be approximately 4.6 billion years old, roughly the same age as our solar system. This makes it significantly older than Oumuamua, which is estimated to be about 1 billion years old, and older than 2I Borisov, estimated at 1.7 billion years. The origin direction was also notable. 3IATLAS was coming from the direction of the galactic center, approaching from the inner regions of the Milky Way. Over its lifetime, it has likely orbited the galaxy multiple times, covering thousands of light years. The journey time was calculated backward. It took approximately 800 million years for 3IATLAS to migrate from the opposite side of the Milky Way's disk to our location. During that time, it was traveling through the vast emptiness of interstellar space, a tiny island of ice and rock in an ocean of nothing. During its passage through our solar system, the European Space Agency responded quickly. ESA's Planetary Defense Office, which normally focuses on objects that might threaten Earth, coordinated observations using telescopes in Hawaii, Chile, and Australia. Even though 3IATLAS posed no danger to our planet, the opportunity to study an interstellar visitor was too valuable to miss. ESA also planned to use its interplanetary spacecraft for observations. Mars Express, which has been orbiting Mars since 2003, was scheduled to observe the visitor during its close approach to Mars on October 3rd. The high-resolution stereo camera and various spectrometers would be trained on this cosmic traveler. The ExoMars Trace Gas Orbiter, another ESA spacecraft orbiting Mars, would also attempt observations. Its color and stereo surface imaging system, normally used to photograph the Martian surface, would instead be pointed at 3IATLAS. The NOMAD spectrometer would try to measure the composition of the comet's tail. Even the Jupiter Icy Moons Explorer, known as JUICE, was scheduled to observe. JUICE was en route to Jupiter, currently on the far side of the Sun from Earth. In November 2025, it would attempt observations using its cameras, spectrometers, and particle sensors. The data wouldn't reach Earth until February 2026 because JUICE was using its high-gain antenna as a heat shield, transmitting at a much lower rate through its medium-gain antenna. The Vera C. Rubin Observatory, still in its science validation phase, had serendipitously imaged 3IATLAS multiple times between June 21st and July 3rd before anyone knew it existed. These images showed a slight increase in the coma diameter over time, providing early evidence of increasing activity as the comet approached the Sun. The timing was fortuitous. If the Rubin Observatory had begun its science validation observations just 2 weeks earlier, it would have discovered 3IATLAS before ATLAS did. The Rubin Observatory, with its enormous field of view and sensitive camera, is expected to revolutionize the detection of interstellar objects once it begins full operations. Estimates suggest that the Rubin Observatory will detect approximately one interstellar object per year. This will transform our understanding of these visitors. Instead of having 3 examples over 8 years, we'll build a catalog, a population study that can answer questions about how common different types of interstellar objects are. As 3 IATLAS approached perihelion, it would pass behind the Sun from Earth's perspective. This meant that during late October 2025, when the comet was closest to the Sun and likely most active, it would be hidden from ground-based telescopes. The glare of the Sun would make observations impossible. The comet would be effectively invisible to us during its most dramatic moment. This occultation by the Sun worried some observers. If something unusual happened at perihelion, like an outburst or fragmentation event, we might miss it. The comet wasn't scheduled to emerge from behind the Sun until late November 2025, offering astronomers another window for observation. The fragmentation risk was real. Comet 2, I-Borisov, the previous interstellar comet, had experienced nucleus fragmentation during its visit. Comets are fragile objects, loosely bound collections of ice and rock. The stress of solar heating, combined with the structural weakness of their material, can cause them to break apart. However, as of late September 2025, no outbursts had been detected in 3 IATLAS. The brightness and activity level appeared steady and predictable. This stability suggested a more robust nucleus, perhaps more tightly bound than Borisov had been. The Gemini Observatory, operating both Gemini South in Chile and Gemini North in Hawaii, obtained spectacular images of 3 IATLAS. On August 27, 2025, the Gemini multi-object spectrograph captured a deep image showing a prominent tail and glowing coma. The image became one of the iconic portraits of this visitor. The Gemini observations were part of a unique educational initiative called Shadow the Scientists. Members of the public, including students from Hawaii and Chile, were invited to remotely join the Gemini South control room via Zoom. They could watch the observations in real time, interact with astronomers, and ask questions about interstellar science. The educational aspect of 3 ATLAS's visit was significant. Here was an object from beyond our solar system, viewable through telescopes, generating real scientific data and capturing public imagination. It provided a tangible connection between cutting-edge research and everyday people interested in the cosmos. The spectroscopic data from Gemini revealed information about the comet's composition and how it was changing as solar heating increased. Different molecules emit light at specific wavelengths, creating distinctive patterns in the spectrum. By identifying these patterns, astronomers could determine what chemicals were present in the coma. Polarimetric observations provided another layer of information. These measurements analyze how sunlight scatters off the dust particles in the coma. Different particle sizes and compositions scatter light differently, creating distinct polarization signatures. Surprisingly, 3 IATLAS showed an extremely deep and narrow negative polarization branch. This is a technical way of saying that the way light scattered off its dust was unlike anything seen in any other comet, whether from our solar system or interstellar. The polarization signature was unprecedented. This unusual polarization suggested that the dust particles in the coma had unique properties. Perhaps they were a different size distribution than typical cometary dust. Perhaps they had a different composition or structure. The finding added another layer to the mystery of this visitor. Interestingly, the optical characteristics of 3 IATLAS resembled those of trans-Neptunian objects and centaurs. These are icy bodies that orbit in the outer reaches of our solar system, far beyond Neptune. The resemblance suggested that 3 IATLAS might have formed in a similar cold environment in its original stellar system. The question of origin became more specific as data accumulated. Where exactly did this object come from? Not just which region of the galaxy, but which star system. Researchers began calculating possible trajectories backward, trying to identify candidate parent stars. The challenge is enormous. 3IATLAS has been traveling for hundreds of millions of years. Stars move during that time, orbiting the galactic center at different speeds depending on their location. The object's path through space has been perturbed by gravitational interactions with countless objects during its journey. Current calculations suggest that 3IATLAS travels a few thousand light-years closer to the galactic center than our Sun does during its orbit. This eccentric galactic orbit took it through regions of varying stellar density, where gravitational perturbations would have nudged its trajectory numerous times. Despite the challenges, the trajectory calculations are important for understanding the diversity of interstellar objects. If 3ATLAS came from an old stellar population in the thick disk, it might have a different composition than objects from younger stars. This could explain some of its unusual properties. Now we must address the elephant in the room. Harvard astronomer Avi Loeb, well known for his unconventional hypotheses about interstellar objects, has suggested that 3IATLAS might not be a natural comet at all. He has proposed, with varying degrees of seriousness, that it could be extraterrestrial technology. Loeb and his collaborators published a paper examining the astrodynamics of 3IATLAS, hypothesizing that it could be technological and possibly hostile, referencing the dark forest hypothesis from science fiction. This hypothesis suggests that the universe might be populated by civilizations that remain hidden because revealing oneself is dangerous. The paper is described by Loeb himself as largely a pedagogical exercise, something fun to explore regardless of its validity. However, it received significant media attention, with headlines suggesting that a Harvard scientist thinks an alien probe might be approaching Earth. Loeb created what he calls the Loeb scale for interstellar objects, ranking them from 0 to 10. 0 means definitely natural, 10 means definitely technological. He initially ranked 3IATLAS as a 6, later adjusting to a 4. These rankings are subjective and not widely accepted by the scientific community. The paper pointed out several statistical curiosities about 3IATLAS. It approaches surprisingly close to Venus, Mars, and Jupiter, with what the authors calculated as a probability of less than 0.005%. The orbital plane's low retrograde tilt relative to the ecliptic was noted as potentially beneficial for hypothetical reconnaissance. The timing of perihelion, when 3IATLAS would be hidden behind the Sun from Earth's perspective, was described as potentially optimal for a reverse solar Oberth maneuver. This is a technique where a spacecraft uses a close pass by the Sun to change its trajectory dramatically while obscured from observation. Loeb suggested that the extreme mass inferred from the lack of trajectory change could indicate something other than a natural comet. He even speculated briefly about a connection to the famous WOW signal, a mysterious radio signal detected in 1977, noting that it came from the direction of Sagittarius, the same general direction 3IATLAS approached from. However, the overwhelming scientific consensus is that 3IATLAS is simply a comet. Tom Statler, NASA's lead scientist for solar system small bodies, stated directly that it looks like a comet, does comet things, and very strongly resembles comets in just about every way. Multiple peer-reviewed scientific papers have analyzed 3IATLAS and consistently concluded that it exhibits all the expected characteristics of an interstellar comet. The presence of water and carbon dioxide ice, the dust coma, the tail, the increasing activity as it approaches the Sun, all point to a natural object. The unusual properties, like the extreme CO2 to water ratio and the large mass, make it an interesting comet, certainly different from most comets in our solar system. But different doesn't mean artificial. The universe is vast and diverse. Finding objects with unusual properties is expected when you're sampling from billions of planetary systems across the galaxy. The statistical arguments about the rarity of large interstellar objects are valid scientific questions. They suggest our models of planetary system formation might need refinement. but extraordinary claims require extraordinary evidence, and there is no evidence that 3IATLAS is anything other than a natural body. Other astronomers have pushed back against the more speculative claims. Jason Wright, an astronomer at Penn State University who works on SETI and technosignatures, wrote a detailed critique explaining what's wrong with some of the more sensational interpretations. His analysis, while respectful, makes clear that the evidence simply doesn't support the technology hypothesis. The public interest in the alien speculation is understandable. The idea of an interstellar probe visiting our solar system is exciting. It captures the imagination in a way that discussions about carbon dioxide ratios do not. But science requires us to follow the evidence, not our hopes or fears. As October 2025 arrived, 3IATLAS made its close approach to Mars. Spacecraft orbiting the red planet attempted observations, though the comet remained quite distant even at closest approach. The data from these observations would provide additional information about the comet's composition and behavior. After passing Mars, the comet continued inward toward perihelion. Ground-based observations became increasingly difficult as the comet's position in the sky moved closer to the sun. By mid-October, it was lost in the solar glare. During this hidden phase, the comet was experiencing maximum solar heating. The rate of sublimation would be increasing dramatically. If the nucleus were going to fragment, this would be the most likely time. But we couldn't see it happen. The comet reached perihelion on October 30th, 2025, exactly as predicted. At that moment, it was 1.356 astronomical units from the Sun, just inside the orbit of Mars, moving at tremendous speed. Then it began its outward journey, its brief visit to the inner solar system complete. As November approached, astronomers prepared for the comet to emerge from behind the Sun. The hope was that it would still be intact and observable, providing more data about how interstellar comets behave as they leave the warmth of a star and return to the cold of interstellar space. The follow-up Shadow the Scientists event at Gemini North in Hawaii was scheduled for November 2025. If the comet survived perihelion, the public would once again be able to participate in real-time observations, watching as astronomers collected data on this departing visitor. After its passage through the inner solar system, 3IATLAS would continue outward, passing through the orbits of the outer planets. Its trajectory would take it past Jupiter in March 2026, though at a considerable distance. Then it would keep going, out toward the realm of Neptune and beyond. Eventually, perhaps in a year or two, 3IATLAS will pass beyond the detection capabilities of even our most powerful telescopes. It will fade from view, becoming once again just another dark object in the vast space between stars. But it will still be there, still moving, still traveling. Where is it going? The trajectory shows it will leave our solar system in the general direction of the constellation Pegasus. It will wander through interstellar space for millions or billions of years more, a frozen time capsule carrying ice formed in another stellar system billions of years ago. Will it ever encounter another star? Possibly. The galaxy is large, but given enough time, most objects eventually pass near another stellar system. Perhaps hundreds of millions of years from now, 3IATLAS will sail through another solar system, be detected by other beings, and spark the same questions it has raised here. The study of interstellar objects is still in its infancy. We have observed exactly 3 confirmed visitors. That's not enough to draw firm conclusions about how common they are, what types exist, or what they can tell us about planetary system formation across the galaxy. Each new interstellar object provides unique information. Oumuamua was bizarre, elongated, tumbling, showing acceleration without visible outgassing, lacking cometary features. It raised more questions than it answered. Some suggested it was a hydrogen iceberg, others thought it might be a fragment of a Pluto-like world, and yes, some speculated about artificial origins. 2I/Borisov was reassuring in its normalcy. It looked like a regular comet, with a coma and tail, behaving exactly as expected. Its composition was studied extensively and found to be similar to, though not identical with, comets from our solar system. It provided evidence that comet formation processes might be universal. 3IATLAS falls somewhere between them. It's definitely active like Borisov, clearly a comet with a coma and tail, but its composition is unusual. Its mass appears anomalously large. Its polarization signature is unique. It's normal enough to be clearly natural, but strange enough to be scientifically fascinating. The three objects suggest that interstellar space contains a diverse population of bodies. Some, like Borisov, are typical comets ejected during planetary system formation. Some, like Oumuamua, are more unusual, perhaps fragments from collisions or objects that lost their volatiles through radiation exposure. And some, like 3ATLAS, are large and compositionally distinct. Researchers Suzanne Falsner and Michelle Bannister have suggested that objects like 3ATLAS could be planet-forming seeds. In this hypothesis, large interstellar objects could become the nuclei around which planets form. Traditional planet formation models struggle to explain how giant planets grow quickly enough before their gas disks dissipate. A ready-made solid object could speed up the process. If this hypothesis is correct, then interstellar objects like 3ATLAS aren't just interesting curiosities. They're important actors in the story of how planetary systems, including potentially our own, came to exist. They're the seeds that can grow into worlds. The chemical composition of 3IATLAS, with its high carbon dioxide content, provides clues about where and how it formed. Carbon dioxide is abundant in cold environments. The high ratio suggests formation in a region where carbon dioxide ice was particularly common or where water ice was depleted for some reason. One possibility is that 3IATLAS formed very far from its parent star, in the cold outer reaches where carbon dioxide remains solid. Another is that it formed closer in, but was later altered by radiation during its interstellar journey. The thick crust hypothesis suggests that radiation processing could have changed the surface properties, locking water beneath while allowing carbon dioxide to escape. The lack of significant water detection doesn't mean water isn't present. It might be locked beneath the surface, unable to sublimate effectively. As the comet ventured deeper into the inner solar system and experienced more intense heating, some researchers hoped to see if water release would increase. The observations planned for when the comet emerged from behind the sun in November would address this question. If water release increased at perihelion, it would suggest that water ice is present but requires more heating to vaporize. If it remained carbon dioxide dominant, it would support the idea of an unusually dry composition. The study of interstellar objects complements other methods of studying exoplanetary systems. We can detect exoplanets through various techniques, measure their masses and orbits, and even analyze the atmospheres of some, but we can't directly sample their material. We can't analyze their chemistry in detail. Interstellar objects offer something unique, actual material from other stellar systems, passing through our neighborhood, available for study with our telescopes and, potentially one day, our spacecraft. They're like messages in bottles, cast into the cosmic ocean by distant shores, carrying information about conditions around other stars. The dream of actually visiting an interstellar object remains challenging. When Oumuamua was discovered, it was already leaving. Any spacecraft mission would have required launch within days and tremendous velocity to catch up. The opportunity was gone before we even knew it existed. For 3IATLAS, the situation was similar. By the time it was discovered and confirmed to be interstellar, it was too close to the sun for any existing spacecraft to reach it in time. The optimal launch window would have been a year before discovery, in July 2024, which obviously wasn't possible. Future missions are being considered. The Initiative for Interstellar Studies has explored concepts for rapid response missions that could be launched quickly when an interstellar object is detected far enough in advance. These would require spacecraft kept in ready state and powerful launch systems capable of high velocities. Another approach is to wait. The Vera-Rubin Observatory, once fully operational, will detect many more interstellar objects. Some will be detected farther out, giving more lead time for mission planning. Eventually, we might have the capability to intercept one of these visitors, return samples to Earth, or even rendezvous and travel alongside it for extended study. Imagine what we could learn from a sample return mission to an interstellar object. We could analyze the isotopic ratios of its elements, determine its precise age, study the organic compounds it contains, examine the effects of interstellar radiation, measure its density and porosity. Each piece of information would tell us something about conditions in another stellar system. The technology required for such missions exists, at least in principle. The challenges are mainly about cost, timing, and political will. If an interstellar object were detected early enough, say when it was still several years from perihelion, a mission could be mounted using conventional propulsion technology. For now, we study these visitors with telescopes. Each new observation adds to our understanding. Each spectrum reveals another molecule, another clue about composition. Each image shows how the activity evolves. Each astrometric measurement refines our knowledge of the trajectory. The professional astronomical community has responded to 3 IATLAS with enthusiasm and rigor. Papers are being written, data is being shared, theories are being developed. This is science at its best, a rare phenomenon observed, data collected, hypotheses tested, and our understanding incrementally improved. The amateur astronomy community has also engaged. While 3 IATLAS was too faint for most amateur telescopes, some dedicated observers with larger instruments were able to spot it. They contributed observations to professional databases, adding to the global effort to characterize this visitor. The public interest has been significant. News articles, social media discussions, YouTube videos, and podcasts have all covered the discovery. People are curious about this cosmic traveler, wondering where it came from and what it means. The fascination with interstellar objects taps into our deep human curiosity about the universe beyond our immediate neighborhood. Educational opportunities abound. Teachers use interstellar objects to teach about orbital mechanics, gravity, spectroscopy, and the nature of comets. The concepts are complex but accessible, providing concrete examples of abstract physics principles. The questions 3 IATLAS raises extend beyond astronomy. What does it mean that objects from other stellar systems regularly pass through ours? How common are these visitors? What can they tell us about the galaxy as a whole? Are there interstellar objects that remain captured in our solar system, now orbiting the sun as permanent refugees from other stars? Some researchers have suggested that a small fraction of objects in the outer solar system might actually be captured interstellar objects. Over billions of years, occasional visitors could have lost just enough velocity during close encounters with planets to become bound to the sun. These would be hiding among the countless asteroids and comets indistinguishable without detailed study. The detection rate will increase dramatically in the coming years. The Vera-Rubin Observatory will systematically scan the entire visible sky every few nights, detecting faint moving objects that would have been missed by previous surveys. The expected detection rate is approximately 1 interstellar object per year, possibly more. This increased detection rate will transform the field. Instead of celebrating each discovery as a rare event, we'll be building statistics. We'll learn about the size distribution, the composition distribution, the orbital characteristics. We'll be able to test theories about planetary system formation against actual data from dozens of examples. Some of those future discoveries will be even more unusual than 3 IATLAS. The galaxy is vast, and the diversity of planetary systems ensures that some truly bizarre objects exist. We might find interstellar objects made primarily of metal, fragments from the collisions of rocky worlds. We might find nitrogen icebergs, like some theories suggest Oumuamua might be. We might find objects that genuinely puzzle us, and perhaps someday we might find something that shows clear evidence of artificial construction, not because of statistical quirks or unusual chemistry, but because of unambiguous signs like radio signals, organized structures, or deliberate trajectory changes. If such an object exists and passes through our solar system during the era of advanced astronomy, we will recognize it. Until that day, if it ever comes, we study the natural visitors with the tools we have. We measure their light, calculate their paths, and wonder about their origins. Each one is a gift, a sample from beyond our solar system, freely delivered to our doorstep. 3I Atlas will be remembered as the third visitor, the massive one, the one with unusual chemistry, the one that sparked both scientific papers and speculation about aliens. It provided valuable data, raised important questions, and reminded us that we are part of a dynamic galaxy where material flows between star systems. As you drift off to sleep tonight, consider that above you, far beyond Earth's atmosphere, billions of objects are wandering through the galaxy. Most will never be detected, never enter any stellar system, never be named or studied. They travel in the darkness between stars, silent and unseen. But occasionally, one passes close enough to a star to be illuminated, close enough to be detected by beings curious enough to look. 3IATLAS was one of these rare moments of intersection between the lonely wanderer and the watchers. Where will it be 1,000,000 years from now? Somewhere between here and there, still traveling, still carrying ice formed in another star's disk billions of years ago, a tiny fragment of deep history moving through an uncaring universe. And where will we be? Perhaps still here, still watching the sky, still wondering what other visitors might pass through. Or perhaps, by then, we'll be the visitors, sending our own artifacts through other stellar systems, objects that might be detected and puzzled over by beings asking the same questions we ask now. The story of 3IATLAS is not finished. Data is still being analyzed. Papers are still being written. The November observations might reveal new surprises. The final accounting of what this object taught us will take years to compile, but its passage through our solar system is temporary. Soon it will be gone, retreating into the darkness from which it came. We will remember it, study the data it provided, and wait for the next visitor. There will be more. There always are. Somewhere out there, right now, another object is approaching. We haven't detected it yet, but it's coming, on a trajectory calculated billions of years ago when it was expelled from its birth system. Eventually, it will pass close enough for our telescopes to see it. And when it does, we'll point our instruments toward it, collect its light, and try to understand where it came from and what it can teach us. Because that's what we do. We watch, we wonder, we study, and slowly, observation by observation, we learn. Sleep well, knowing that the universe is stranger and more wonderful than we imagine, full of travelers and mysteries, some of which pass right through our cosmic neighborhood, close enough to touch with light, if not with hands. The visitor has come and will soon go, but the questions it raised will remain, challenging us to better understand the galaxy we inhabit and our place within it. But let's not end there. There's so much more to understand about this visitor, about the methods we use to study it, and about what it means for our understanding of the cosmos. The Atlas survey system that discovered 3IATLAS is itself a remarkable achievement. It consists of 4 telescopes spread across the globe, 2 in Hawaii, 1 in Chile, and 1 in South Africa. Each telescope automatically scans the entire visible sky multiple times every night. They're not looking for beauty or artistry, they're looking for change, for movement, for anything that wasn't there the night before. The telescopes work in a coordinated network. When one telescope detects something interesting, the others can quickly verify it. This redundancy is crucial because false alarms are common. Cosmic rays hitting the detector can mimic a moving object, Satellite glints can fool the software. Asteroids from our own solar system vastly outnumber interstellar visitors. The software that analyzes ATLAS images processes millions of data points every night. It compares each new image to a reference image of the same patch of sky, looking for differences. Stars should appear in the same locations night after night. Anything that moves, appears, or disappears gets flagged for human review. Larry Deno, the ATLAS team member who reviewed and submitted the discovery observations, described the process as both exciting and cautious. They've had false alarms before, objects that initially looked interesting but turned out to be something mundane. So when 3 IATLAS first appeared, there was careful verification before any announcement. The moment when an interstellar object is confirmed is surprisingly undramatic. It's not a eureka moment with shouting and celebration. It's more like a slow realization as observation after observation confirms what the initial data suggested. The orbital calculations become increasingly precise, the uncertainty decreases, and eventually the conclusion becomes unavoidable. This object came from beyond. The Minor Planet Center, located at the Smithsonian Astrophysical Observatory, serves as the central clearinghouse for observations of asteroids and comets. When Atlas reported their observations of 3 IATLAS, the data went to the MPC, which issued a circular to the global astronomical community. Within hours, telescopes worldwide were being redirected. This rapid mobilization reveals something important about modern astronomy. It's a global, collaborative enterprise. Data is shared immediately. Observations are coordinated. No single nation or institution owns the discovery. The object belongs to humanity's shared knowledge. The technical challenges of observing 3 IATLAS evolved as it moved through the solar system. When it was first discovered at 4.5 astronomical units from the Sun, it was faint, requiring long exposure times. As it approached, it brightened, but also moved faster across the sky, requiring different observing strategies. Tracking a fast-moving object through a telescope is not trivial. Most telescopes are designed to track at the sidereal rate, compensating for Earth's rotation to keep stars fixed in the field of view. To track a comet, the telescope must move at a different rate, causing the stars to trail while the comet remains sharp. For 3 IATLAS, the tracking rate changed continuously as its velocity and direction changed. Sophisticated software calculated the predicted position at any given time, but small errors in the orbital solution could cause the object to drift out of the field of view during long exposures. The brightness of 3 IATLAS peaked at around magnitude 10 to 11, far too faint to see with the naked eye or even binoculars. You needed at least a modest telescope, and even then, it appeared as nothing more than a fuzzy gray smudge, hardly dramatic to the eye. All the real information came from long photographic exposures and spectroscopic analysis. Photography in astronomy is not like photography on Earth. A single exposure might last minutes or even hours, accumulating photons from faint objects. The detector is not film, but a CCD or CMOS sensor, cooled to reduce thermal noise. Each pixel counts the number of photons that hit it, building up a signal gradually. The spectrographs that analyzed 3 IATLAS's light are marvels of optical engineering. Light from the comet is collected by the telescope and directed into an instrument that splits it into its component wavelengths. This can be done with a prism or, more commonly, with a diffraction grating. The resulting spectrum is then recorded by a detector. What emerges is a graph showing intensity versus wavelength. Different molecules absorb or emit light at specific wavelengths, creating distinctive patterns. Water shows features at certain infrared wavelengths. Carbon dioxide shows others. Cyanogen creates recognizable lines in the visible spectrum. Reading a spectrum is like reading a chemical barcode. Each substance has its unique signature. By comparing the observed spectrum to laboratory measurements of known molecules, astronomers can determine what's present in the comet's coma. The James Webb Space Telescope brought unprecedented sensitivity to this analysis. Operating in the infrared, where many important molecular features appear, Webb could detect molecules that would be invisible to optical telescopes. Its resolution allowed it to distinguish between different regions of the coma, mapping the distribution of molecules. The SPHEREX mission, observing from Earth orbit, added wide-field imaging in multiple infrared wavelengths, while Webb could study 3 IATLAS in exquisite detail. SPHEREX could map the entire extent of its coma, revealing the overall structure of the dust and gas cloud. Ground-based telescopes contributed crucial data. The Very Large Telescope in Chile, consisting of 4 8.2-meter mirrors, provided high-resolution spectroscopy. The Gran Telescopio Canarias, with its 10.4-meter mirror, captured detailed images showing the coma's structure. Each telescope has strengths. Space telescopes avoid atmospheric distortion and can observe wavelengths blocked by Earth's atmosphere, but they're expensive and have limited observing time. Ground-based telescopes are more accessible and can dedicate nights to a single object, but they must contend with weather, atmospheric turbulence, and the day-night cycle. The international cooperation extended beyond professional observatories. Amateur astronomers with sophisticated equipment contributed observations. These amateur measurements, while less precise than professional data, added to the temporal coverage, filling gaps when professional telescopes were pointed elsewhere. The data from all these sources flowed into databases accessible to researchers worldwide. Anyone with the appropriate credentials could download the observations and perform their own analysis. This open access model accelerates discovery by allowing multiple teams to work independently on the same problem. Different research groups focused on different aspects. Some studied the composition, others analyzed the dust properties. Some worked on refining the orbital solution. Others modeled the comet's thermal evolution. Each group published their findings, adding pieces to the puzzle. The peer review process ensures quality control. Before publication, each paper is evaluated by experts who check the methodology, verify the conclusions, and identify potential errors. This process isn't perfect, but it helps maintain scientific standards. The papers about 3 IATLAS span a range of topics and technical sophistication. Some are observational reports presenting data with minimal interpretation. Others are theoretical papers using models to explain the observations. Still others are review papers, synthesizing multiple studies into a coherent picture. Reading these scientific papers reveals the careful, measured language of professional astronomy. Claims are hedged with uncertainties. Conclusions are provisional, subject to revision as new data arrives. The tone is formal, objective, devoid of the excitement that often accompanies discovery. But behind that formal language are human beings, researchers who dedicated years to studying comets, who compete for telescope time, who experience both the frustration of cloudy nights and the thrill of detecting a new molecule. Science is a human endeavor, even when it concerns objects billions of years old. The career path that leads someone to study interstellar objects is long and demanding. It typically begins with undergraduate training in physics or astronomy, followed by graduate school where research skills are developed. A PhD might take 5 to 7 years. Then comes postdoctoral positions, temporary research jobs that allow young scientists to build their publication record. Only after a decade or more of training might a researcher secure a permanent position. And even then, the competition for telescope time, grants, and recognition is intense. The scientists studying 3 IATLAS represent thousands of accumulated hours of training and expertise. Some of these researchers had been preparing for years for the next interstellar object. After 2 Borisov in 2019, the community knew another visitor would eventually appear. Plans were made. Observing proposals were written, ready to be submitted as soon as a discovery was announced. When 3 IATLAS appeared, these researchers were ready. The study of interstellar objects sits at the intersection of multiple scientific disciplines. It involves orbital dynamics, a branch of physics concerned with how objects move under gravitational influence. It involves spectroscopy, the study of how matter interacts with electromagnetic radiation. It involves chemistry, understanding what molecules exist and how they form. It also involves instrumentation, the design and construction of telescopes and detectors. It involves data analysis, using statistical methods to extract signal from noise. It involves computational modeling, simulating how comets behave under different conditions. No single person understands all these aspects deeply. Modern astronomy is collaborative because it must be. The problems are too complex for individual researchers. Teams form, bringing together experts in different areas, each contributing their specialized knowledge. The physical processes occurring in 3IATLAS are complex. As sunlight warms the nucleus, ice beneath the surface absorbs energy. When the temperature reaches the sublimation point, the ice transforms directly from solid to gas, bypassing the liquid phase. This gas, expanding rapidly, escapes through cracks and pores in the surface. As the gas escapes, it carries dust particles with it. These particles, freed from the ice that bound them, are pushed outward by radiation pressure from sunlight. Smaller particles are pushed more effectively than larger ones, creating a size-dependent separation as the dust travels away from the nucleus. The gas coma extends much farther than the dust coma. Gas molecules move quickly at hundreds of meters per second and can travel millions of kilometers before being ionized by solar radiation or dissociated by ultraviolet light. The dust, heavier and slower, forms a more compact cloud. The tail of a comet has two components. The dust tail, yellowish and curved, follows the comet's orbital path, lagging behind because the dust particles are still moving in the comet's original direction, even as radiation pressure pushes them. The ion tail, bluish and straight, points directly away from the sun, created by ionized gas molecules pushed by the solar wind. 3IATLAS displayed both types of tails, though the ion tail was more prominent in some observations. The relative strength of these tails depends on the composition of the coma and the intensity of solar radiation at the comet's distance. The dust particles themselves vary in composition. Some are primarily silicates, rocky minerals that remain solid even at high temperatures. Others are carbonaceous, rich in organic compounds. Some might be mixtures, complex aggregates formed in the cold disk around the comet's parent star. The organic compounds detected in comets are of particular interest because they might be similar to the prebiotic molecules that seeded life on Earth. Comets bombarding the early Earth could have delivered water and organic molecules, providing the raw materials for biology. Whether 3IATLAS carries such molecules is unknown. Detecting complex organics requires detailed spectroscopy, looking for the characteristic signatures of different molecular bonds. Some observations hinted at organic material, but conclusive identification requires data that might not be available until more observations are analyzed. The rotation of the nucleus affects what we observe. As the nucleus spins, different regions face the sun at different times. If the nucleus is irregularly shaped or has compositional variations across its surface, the outgassing rate will vary with rotation. This creates periodic variations in brightness and gas production. Unfortunately, determining the rotation period of 3IATLAS from the available data proved challenging. The object was too faint and the variations too subtle for a definitive measurement. Estimates suggested a rotation period of hours to days, but the uncertainty was large. The nucleus shape is also uncertain. Is it elongated like Oumuamua, roughly spherical like many comets, potato-shaped? Without resolved images of the nucleus itself, we can only infer shape from how the brightness changes with rotation, and those measurements were inconclusive for 3IATLAS. What we do know is that the nucleus is massive and relatively inactive for its size. A smaller nucleus with the same gas production would show much larger non-gravitational acceleration. A larger nucleus with the same acceleration would be producing far more gas. The observations point to a large, relatively sluggish nucleus. This sluggishness might indicate a thick crust insulating the interior. Comets develop crusts as they age. Repeated heating cycles cause the most volatile ices to sublimate, leaving behind a layer of dust and less volatile material. This crust can be several meters thick, effectively insulating the pristine ice beneath. For an interstellar object, the crust could be even thicker. During its journey through interstellar space, cosmic rays would have bombarded the surface continuously for millions or billions of years. This radiation processing can alter the surface chemistry, creating complex molecules that don't sublimate easily. Alternatively, 3IATLAS might simply have formed with less volatile ice than typical comets. If it formed in a warmer region of its parent disk, or if that disk had unusual composition, the object might naturally be less active. The comparison with 2I/Borisov is instructive. Borisov appeared to be a relatively normal comet, behaving much like comets from our solar system. Its activity level was consistent with its size. Its composition, while not identical to solar system comets, was similar enough to suggest similar formation processes. 3IATLAS is different. Its high CO2 to water ratio sets it apart. Its large mass combined with modest activity is unusual. Its polarization signature is unique. These differences suggest that conditions in its birth system were different from what produced Borisov or our solar system's comets. This diversity is important. If all interstellar objects were identical, we'd learn that planetary system formation is highly uniform. But the variety we're seeing suggests that different stellar systems produce different populations of comets, shaped by local conditions like the star's mass, the disk's composition, and the dynamics of planet formation. The third comparison point is Oumuamua, which remains the most controversial. Its extreme elongation was unlike any solar system object. Its non-gravitational acceleration without visible coma was puzzling. Various explanations have been proposed: a hydrogen iceberg, a nitrogen iceberg, a fragment of a larger body, even the solar sail hypothesis. Recent research suggesting that hydrogen ice, formed by radiation processing of water ice, could explain Oumuamua's behavior has gained traction. In this model, Oumuamua was once a normal comet-like object, but billions of years in interstellar space converted surface water ice into molecular hydrogen trapped in the ice matrix. When heated by the sun, this hydrogen outgassed, creating acceleration without a visible coma. If this explanation is correct, it suggests that very old interstellar objects might behave differently from younger ones. 3ATLAS, estimated to be 4.6 billion years old, has apparently not undergone the same transformation. Perhaps its larger size protected the interior, or perhaps it spent less time in regions of intense cosmic ray flux. The age estimates for these objects come from their galactic orbits. By tracing their paths backward and seeing how far they've strayed from the galactic plane, researchers can estimate how long they've been wandering. Older objects have had more time to be perturbed by gravitational encounters, causing them to stray farther vertically. These age estimates are statistical, not absolute. An individual object might have an unusual history that makes it appear older or younger than it actually is. But on average, the method works, and the results suggest that 3IATLAS is ancient, roughly as old as the solar system itself. This means that 3IATLAS formed around a star that existed 4.6 billion years ago. That star has since moved through the galaxy, orbiting the galactic center multiple times. It might still exist, a middle-aged star like our Sun, or it might have died if it was more massive and burned through its fuel more quickly. Wherever that star is, it doesn't know that one of its children has wandered through another star's domain. The information can't travel fast enough. Even if someone in that system were watching, they wouldn't know for millions of years that 3IATLAS passed through the solar system. This temporal isolation is one of the strange features of the universe. Events can be causally disconnected simply because of distance and the finite speed of light. By the time anyone could learn what happened here, 3IATLAS will have moved on, and our solar system will have shifted position, and the galaxy will have rotated slightly. The scale of galactic motion is difficult to grasp. Our solar system orbits the galactic center at about 220 kilometers per second. At this velocity, it takes roughly 225 million years to complete one orbit. Since the solar system formed, it has orbited the galaxy about 20 times. During each orbit, the solar system moves through different neighborhoods. Sometimes it passes through spiral arms, regions of active star formation where supernovae are more common. Sometimes it traverses quieter regions between the arms. Each environment has different radiation levels, different densities of interstellar gas, different populations of nearby stars. 3IATLAS has experienced a similar journey, though starting from a different location. It has drifted through various regions of the galaxy, sometimes passing near star clusters, sometimes sailing through empty space between stars. Each region has left its mark, subtly altering the object through radiation exposure and, very rarely, through gravitational encounters. The probability of a close encounter between an interstellar object and a star is extremely low. Space is vast, and stars are tiny targets. Most interstellar objects will wander for billions of years without passing through any stellar system. The fact that we've detected 3 in 8 years suggests that our solar system, or more accurately, our sun's gravitational well, captures them temporarily as they pass through. The distribution of interstellar objects in the galaxy is likely not uniform. Regions near star-forming clouds, where planets are being born and objects are being ejected, probably have higher densities. Older, quieter regions might have lower densities. Our location in the galaxy, in a relatively calm suburban region, might see fewer visitors than regions closer to the galactic center. Nevertheless, estimates suggest that at any given moment, thousands of interstellar objects are passing through the solar system at various distances. Most are far beyond Neptune, completely undetectable with current technology. A few are closer, within the orbits of the giant planets, but still too faint or too distant to see. The ones we detect are the closest, brightest, or largest. They represent a biased sample, the tip of an iceberg of objects that remain invisible. Future surveys with more sensitive instruments will detect fainter objects, gradually revealing the true population. The Vera C. Rubin Observatory will be particularly important. Its 8.4-meter mirror and enormous field of view will allow it to image the entire visible sky every few nights, detecting objects as faint as magnitude 24. This sensitivity should reveal interstellar objects much smaller than 3IATLAS. The Legacy Survey of Space and Time, or LSST, which the Rubin Observatory will conduct, will generate enormous amounts of data. Each night of observing will produce tens of terabytes of data. Over its planned 10-year survey, it will catalog billions of objects. Processing this data requires sophisticated algorithms. Machine learning systems will classify objects automatically, flagging anything unusual for human review. The challenge is managing the scale. With billions of objects tracked, even a tiny false positive rate will generate thousands of spurious alerts. Differentiating between solar system objects and interstellar objects will become routine, but still requires careful analysis. Solar system asteroids can have highly elliptical orbits that might initially look hyperbolic due to measurement uncertainty. Only with multiple observations over time can the true orbital parameters be determined with confidence. The discovery rate of one interstellar object per year predicted for the Rubin Observatory is conservative. It might be higher if the population is denser than expected, or lower if we've been lucky with our first 3 detections. But even at 1 per year, within a decade we'll have a substantial catalog. With 10 or more examples, patterns will emerge. We'll learn about the typical size distribution, the range of compositions, the variety of activity levels. We'll be able to compare populations from different regions of the galaxy if we can determine their origins with sufficient precision. Some interstellar objects might be entirely unexpected. Perhaps we'll find one made primarily of water ice, a giant snowball from a system rich in volatiles. Perhaps we'll find metal-rich objects fragments from the collision of rocky planets, perhaps we'll find objects with such unusual properties that they challenge our current theories. And perhaps, just perhaps, we'll find one that truly is artificial. Not because we want to, or because it would be exciting, but because the evidence genuinely points in that direction. If such an object exists and passes through our solar system, the Rubin Observatory might detect it. What would constitute convincing evidence of artificiality? Probably not size or brightness or unusual composition. All of those can be explained naturally, even if the explanations are sometimes stretched. The convincing evidence would be behavior that can't be explained by natural processes. A deliberate trajectory change using propulsion would be definitive. If an object changed its velocity in a way that couldn't be explained by outgassing or gravitational perturbations, if it adjusted its course as if navigating, that would be difficult to dismiss. Radio emissions with structured information would also be compelling. Natural processes generate radio waves, but they're random noise. A repeating pattern, especially one containing information, would strongly suggest technology. Optical signaling, flashes of light in a pattern, would similarly indicate intelligence. Natural objects can vary in brightness, but deliberate signaling has characteristics that distinguish it from natural variation. None of these have been observed in 3IATLAS or any other interstellar object. The behaviors we see are entirely consistent with natural comets and asteroids. The speculation about artificial origins remains just that, speculation without supporting evidence. The appeal of the artificial hypothesis is understandable. The discovery of extraterrestrial intelligence would be one of the most profound moments in human history. It would answer the question of whether we're alone in the universe. It would provide evidence that life and intelligence arise elsewhere under different conditions. But the universe doesn't care what we find appealing. The evidence dictates our conclusions, not our hopes, and the evidence, overwhelming and consistent, indicates that 3IATLAS is a natural object, a large comet from another star system, interesting in its own right without requiring extraordinary explanations. The scientific method requires skepticism, particularly for extraordinary claims. The bar for accepting the artificial hypothesis is appropriately high, not because scientists are closed-minded, but because false positives in such matters would be catastrophic for public trust in science. Imagine if the astronomical community announced the detection of an alien probe only to have it turn out to be a natural object. The embarrassment would be severe. Public trust in astronomical pronouncements would be damaged. Future genuine discoveries might be dismissed as more false alarms. So scientists are cautious, perhaps excessively so. They require multiple independent lines of evidence before accepting unusual claims. They prefer to exhaust natural explanations before considering artificial ones. This conservatism frustrates some, but it's essential for maintaining credibility. The criticism of Avi Loeb's more speculative claims comes not from a desire to suppress unconventional ideas, but from concern about methodology and evidence standards. Science thrives on unconventional ideas, but those ideas must be supported by data and testable by independent researchers. The debate over 3IATLAS nature, while sometimes contentious, is ultimately healthy for science. It forces researchers to articulate clearly why they believe it's natural, to examine the evidence carefully, and to consider what observations would change their minds. This process strengthens our understanding. As November 2025 arrived and 3IATLAS emerged from behind the sun, new observations began. The comet had survived perihelion intact, still visible, still active. The post-perihelion observations would reveal whether the close solar approach had altered its activity level or composition. Some comets brighten dramatically after perihelion as newly exposed ice begins sublimating. Others fade quickly, their most volatile materials exhausted. The behavior of 3IATLAS in the weeks after perihelion would provide clues about its internal structure and composition gradient. The observations also addressed another question: had the nucleus fragmented? Comets sometimes break apart during perihelion passage. the stress of heating and rotation overcoming the weak forces holding the nucleus together. If 3 IATLAS had fragmented, multiple separate nuclei would be visible, each with its own coma. Initial post-perihelion observations showed no clear evidence of fragmentation. The object appeared as a single source with an elongated coma and tail. This suggested a relatively robust nucleus, not the loose rubble pile that sometimes falls apart under stress. The spectroscopic observations continued, tracking how the composition changed as the comet receded from the sun. Would the CO2-dominated outgassing continue, or would water begin to dominate as surface ice was depleted? The answer would constrain models of the nucleus structure. As the comet moved outward, it would gradually fade, becoming harder to observe. By early 2026, only the largest telescopes would be able to detect it. By mid-2026, it might be too faint even for them. The window of opportunity for detailed study would close. The data collected during this brief encounter will be analyzed for years. New techniques will be applied to old observations. Patterns might emerge that weren't apparent during the initial analysis. The scientific return from 3ATLAS will continue long after the object itself fades from view. Future interstellar objects will be compared to 3IATLAS. Is its high CO2 ratio unique, or will others show similar chemistry? Is its large mass anomalous, or are there many massive interstellar bodies? Each new detection will either confirm that 3IATLAS is an outlier or show that it represents a common class. The legacy of 3IATLAS extends beyond astronomy. Its discovery captured public imagination, bringing attention to the reality of interstellar objects. People who might never have thought about what lies between the stars became aware that we're not isolated, that material from other stellar systems visits regularly. Educational programs use 3IATLAS as a case study. Students learned about orbital mechanics by calculating its trajectory. They learned about spectroscopy by understanding how we determine composition. They learned about the scientific method by following how hypotheses about its nature were tested and refined. The philosophical implications are subtle but profound. We live in a galaxy where matter moves between stellar systems. The building blocks of planets aren't confined to their birth systems. Material mixes and spreads, carrying with it the chemical signatures of diverse environments. This means that some of the atoms in your body might have originated in other stellar systems. Material from interstellar space has been falling onto Earth for billions of years. Most of it is microscopic dust, but occasionally larger objects impact. Some of those larger objects might have been interstellar, though proving it after the fact is nearly impossible. The meteorites in museum collections came from our solar system, primarily from the asteroid belt, but statistically, some objects from other stars should have hit Earth over its 4.6 billion year history. Those impacts left no distinguishing marks. The material was incorporated into Earth's mass, indistinguishable from native material. Perhaps someday we'll find a meteorite with isotopic ratios that clearly mark it as interstellar. Such a discovery would provide a physical sample from another stellar system, available for detailed laboratory analysis. The information content would be enormous. Until then, we study the fleeting visitors while they're accessible. We point our telescopes skyward, collect their light, and try to read the messages encoded in the photons. Each observation is a conversation across space and time, a dialogue between the present and the ancient past when these objects formed. 3IATLAS formed when our solar system was young. Earth was still being bombarded by impactors. The moon was closer and appeared larger in the sky. Life was just beginning to organize itself into complex forms. In that distant epoch, in another stellar system, gas and dust collapsed to form a comet nucleus. That nucleus orbited its parent star for some time, perhaps millions of years. Then something happened, a gravitational perturbation, perhaps from a passing planet or a nearby star, changed its orbit. The nucleus was flung outward, escaping its birth system, beginning a journey that would last billions of years. Through all that time, it traveled. past other stars, though none close enough to significantly alter its path, through clouds of interstellar gas, though too diffuse to notice, across the galaxy, slowly orbiting the galactic center along with billions of other objects. And then, in July 2025, it passed close enough to our sun to be illuminated and detected. For a few months, it was visible to our telescopes, a brief window in an eon-long journey. We observed it, measured it, studied it, and wondered about it. Soon, it will leave, returning to the darkness from which it came. The solar system will continue its orbit around the galaxy. Life on Earth will continue evolving. Civilizations will rise and perhaps fall. And 3IATLAS will be somewhere else, moving through the galaxy, possibly approaching another star. Will anyone be there to see it? Will beings in that other system point their instruments toward it and wonder where it came from? Will they calculate that it passed through a stellar system called the Sun, orbited by a planet called Earth, where conscious beings looked up and saw them reflected in a traveler from afar? We can't know. The distances are too vast, the timescales too long, but it's pleasant to imagine that connection, that possibility of mutual recognition across the ages, mediated by a silent chunk of ice and rock that visited both. For now, 3IATLAS continues its journey. Above us, beyond the atmosphere, beyond the moon, beyond the planets, it moves through the solar system, indifferent to our attention, following the gravitational paths laid out billions of years ago. And we watch, as humans have always watched the sky, trying to understand, trying to find meaning, trying to place ourselves in the vast context of cosmic time and space. The visitor reminds us that we're part of something larger, that our solar system is connected to the galaxy, that we're all made of the same materials, forged in the same stellar furnaces, distributed by the same cosmic processes. Sleep now with the knowledge that above you, the universe continues its ancient dance. Objects move through the darkness. Light travels between stars. And occasionally, just occasionally, a visitor from another system passes close enough for us to see it, to study it, and to wonder about the worlds from which it came. The story of 3IATLAS is the story of cosmic wandering, of matter in motion, of the patient processes that shape the galaxy over billions of years. It's a story without a clear ending, because the object continues, will continue, long after we're gone, long after our civilization has become as ancient history as the Sumerians are to us. But for this brief moment, we shared space with it. We observed it. We learned from it. And in doing so, we learned something about ourselves, about our capabilities, about our place in the universe, and about the nature of the cosmos we inhabit. Let's linger a bit longer on the details, on the methods we use to understand these visitors, on the history that brought us to this moment of capability. The story of detecting objects in our solar system goes back centuries. In 1705, Edmund Halley noticed that comets observed in 1531, 1607, and 1682 had remarkably similar orbits. He proposed they were the same object, returning periodically, and predicted it would return in 1758. He died before seeing his prediction confirmed, but when the comet appeared on schedule, it was named in his honor. That prediction marked a turning point. Comets were no longer omens or supernatural phenomena. They were objects following predictable paths, governed by the same laws of physics that governed planets. The universe became knowable, calculable, a place where mathematics could predict the future. For the next 2 centuries, astronomers cataloged comets, calculated their orbits, and classified them. Periodic comets like Halley's were distinguished from non-periodic comets that appeared once and never returned. But all of them, without exception, were bound to the sun. Their orbits were ellipses, sometimes highly elongated, but always closed loops. The possibility of interstellar objects was discussed theoretically. If comets could be ejected from other stellar systems, they should occasionally pass through ours, but detecting them was another matter. They would be faint, fast-moving, and nearly indistinguishable from solar system comets until their orbits were precisely measured. The search required systematic surveys of the sky, something that became practical only with modern CCD cameras and automated telescopes. The Pan-STARRS survey in Hawaii, operational since 2010, was designed to scan for near-Earth asteroids but had the capability to detect interstellar visitors. When Pan-STARRS discovered Oumuamua in October 2017, it was initially classified as a comet, then as an asteroid, before the peculiar orbit revealed its interstellar origin. The astronomical community was electrified. After centuries of theoretical possibility, we finally had confirmation. Interstellar objects do visit our solar system. The naming caused some confusion. Oumuamua is a Hawaiian word meaning scout or messenger, appropriate given the discovery location. The official designation 1/2017 U1 marked it as the first interstellar object, discovered in the second half of October 2017. The letter I was added to the classification scheme specifically for interstellar objects. 2 years later, amateur astronomer Gennady Borisov discovered 2I/Borisov using his homemade telescope in Crimea. Unlike Oumuamua, which was discovered while leaving, Borisov was detected while approaching, giving astronomers months to study it intensively. The resulting observations showed a comet that was strange in being from another star system, but otherwise rather ordinary in behavior. By the time 3IATLAS appeared in 2025, the astronomical community was more prepared, the procedures were established, the observation networks were ready, and the scientific questions were better formulated. Yet 3IATLAS still surprised us with its unusual properties. The Atlas system itself represents decades of technological development. Each telescope has a primary mirror measuring 0.5 meters in diameter, modest by modern standards, but they're paired with very wide field cameras that can image large sections of sky in single exposures. This combination makes them excellent for detecting moving objects. The cameras use large CCD arrays, millions of pixels arranged in a grid. Each pixel acts as a tiny light bucket, accumulating photons during an exposure. After the exposure, the accumulated charge in each pixel is read out, converted to a digital number representing the brightness at that location. These images are enormous files, containing detailed information about millions of stars and galaxies. Processing them requires substantial computing power. The software must identify every point source, measure its position and brightness, and compare it to previous images of the same field. Most objects don't move between exposures, separated by a few hours or days. They're stars, too distant for their motion to be noticeable on human timescales. But solar system objects do move, their positions shifting noticeably against the background stars. This motion is what the software detects. The challenge is distinguishing between different types of moving objects. Near-Earth asteroids move rapidly across the sky and might appear in different positions in consecutive exposures. Main belt asteroids move more slowly. Comets beyond Jupiter move slower still. And interstellar objects have unique motion characteristics depending on their velocity and direction. When 3IATLAS was first detected, the software flagged it as a moving object but couldn't immediately determine its nature. That required orbital calculations based on multiple observations. As more data points accumulated, the orbit became better defined and its interstellar origin became clear. The orbital calculations themselves involve sophisticated mathematics. Newton's laws of motion and gravity provide the foundation, but the actual solar system is complex. The sun dominates gravitationally, but the planets also exert forces. Even small bodies like asteroids can perturb an object's path slightly if it passes close enough. For 3IATLAS, the dominant forces were solar gravity and, to a lesser extent, Jupiter's gravity when it passed relatively nearby. The calculated trajectory accounts for all these influences, producing predictions of where the object will be at any future time. The precision of these predictions depends on the accuracy of the observations and how well we know the masses and positions of all the perturbing bodies. The uncertainty in 3 IATLAS's perihelion time was just 2 minutes. Think about that. For an object that's been traveling through space for billions of years, we can predict when it will reach its closest point to the Sun to within 120 seconds. This precision demonstrates the power of celestial mechanics and the quality of modern observations. Of course, this precision applies only to the gravitational forces. Non-gravitational forces like outgassing are harder to predict because they depend on the comet's rotation, surface properties, and composition, all of which are poorly known. For 3 IATLAS, the non-gravitational acceleration was too small to measure, simplifying the calculations. The Hubble Space Telescope observations of 3 IATLAS required careful planning. Hubble orbits Earth every 95 minutes, spending part of each orbit in Earth's shadow and part in sunlight. Observations must be scheduled during the sunlit portions, and targets must be positioned where Earth doesn't block the view. For a moving target like 3 IATLAS, the planning is more complex. The spacecraft must track the comet's motion, adjusting pointing continuously during the exposure. The guide stars used to maintain stable pointing must be carefully selected to ensure they remain in the field of view. Hubble's instruments have different capabilities. The Wide Field Camera 3, used for many 3 IATLAS observations, can image in ultraviolet, visible, and near-infrared wavelengths. Different filters select specific wavelength ranges, allowing astronomers to study how the comet's brightness varies with wavelength, revealing information about composition and dust properties. The resulting images show the coma as a fuzzy, asymmetric blob with a brighter center and fainter outer regions. The asymmetry reveals the direction of the Sun and the preferential ejection of dust in certain directions. The brightness gradient shows how dust density decreases with distance from the nucleus. Deep analysis of these images can reveal fine structure, jets of material streaming from active regions on the nucleus, spiral patterns created by rotating emission sources, variations in brightness that might indicate coma pulsations or rotational modulation. For 3 IATLAS, the most striking visual feature was the teardrop shape, with a bright head and a gradually fading tail extending in the anti-solar direction. This classic cometary appearance confirmed that despite its unusual chemistry, it was fundamentally similar to other comets in its physical behavior. The James Webb Space Telescope brought different capabilities. Webb operates entirely in the infrared, from wavelengths of 0.6 microns, just at the edge of visible red, to 28 microns, deep in the mid-infrared. This wavelength range is perfect for studying molecules because many important molecular vibrations produce spectral features in the infrared. Webb's primary mirror is 6.5 meters in diameter, composed of 18 hexagonal segments that work together as a single surface. This large aperture provides excellent light-gathering power and angular resolution, allowing detailed spectroscopy even of faint objects. The near-infrared spectrograph, or NIRSPEC, can observe in multiple modes. For 3 IATLAS, it likely used a fixed slit mode, where light from the comet passes through a narrow slit and is dispersed by gratings into a spectrum. The spectrum is then recorded by sensitive infrared detectors cooled to just a few degrees above absolute zero. The resulting spectrum of 3 IATLAS showed clear absorption features from water ice and carbon dioxide ice, along with other molecules in smaller quantities. The depth and shape of these features allow astronomers to determine not just what molecules are present, but their temperature, velocity, and relative abundances. The extreme CO2 to H2O ratio measured by Webb was the most striking finding. In most comets, water dominates. The ratio is typically 10 or more water molecules for every CO2 molecule. 3 IATLAS showed the inverse, 8 CO2 molecules for every water molecule. This is nearly unprecedented. Why such a difference? The leading theories involve either formation location or surface processing. If 3 IATLAS formed in an unusually cold region of its parent disk, far from the star where carbon dioxide is abundant, it might naturally have this composition. Alternatively, if radiation processing during its interstellar journey created a crust that preferentially seals in water while allowing CO2 to escape, the observed ratio could result from this filtering effect rather than the bulk composition. Distinguishing between these possibilities requires modeling. Researchers create computer simulations of comet formation under different conditions, predicting the resulting compositions. They also model radiation processing, calculating how cosmic rays alter surface chemistry over time. Comparing these model predictions to the observations helps constrain what actually happened. The modeling is complex because many parameters are uncertain. What was the temperature profile in the parent disk? How much CO2 was available during formation? What is the porosity of the nucleus, affecting how radiation penetrates? How long did the object spend in regions of high cosmic ray flux? Each parameter choice produces different predictions. The art of modeling is finding the combination of parameters that best matches all the observations while remaining physically plausible. It's a process of iteration and refinement, gradually narrowing the possibilities. The Very Large Telescope's observations added to this picture. Located at Cerro Paranal in Chile's Atacama Desert, at an altitude of 2,635 meters, the VLT consists of 4 8.2-meter unit telescopes and 4 movable 1.8-meter auxiliary telescopes. For 3 IATLAS observations, the unit telescopes were primarily used. The VLT's UVES spectrograph, which stands for ultraviolet and visual Echelle spectrograph, provided high-resolution spectroscopy in the visible wavelength range. This instrument can resolve spectral features separated by just thousandths of a nanometer, allowing precise measurements of molecular line profiles. From these observations, astronomers detected cyanogen, CN, a molecule consisting of carbon and nitrogen atoms. Cyanogen is common in cometary comae, produced by the breakdown of larger molecules. Its presence confirms that 3-IATLAS contains carbon and nitrogen, building blocks of organic chemistry. Nickel emission was also detected, a more unusual finding. Metallic atoms in cometary comae have been known for decades, but they're typically present in very small quantities. Nickel, along with iron, comes from the dust particles, tiny grains that include metallic components from the original material out of which the comet formed. The detection of these atoms requires looking at very specific wavelengths where they emit light. When gas molecules in the coma are ionized by solar ultraviolet radiation, they can fluoresce, emitting light at characteristic wavelengths. Each element and molecule has its own spectral fingerprint, and by looking for these fingerprints, astronomers can conduct a chemical census of the coma. As 3-IATLAS approached perihelion, the activity level was predicted to increase. More sunlight means more heating, more sublimation, more gas production. The rate of increase depends on the composition. Water-ice sublimation accelerates rapidly inside about 3 astronomical units. Carbon dioxide sublimation is already significant at much larger distances. The observations showed increasing activity, but not as dramatically as some predictions suggested. This relatively modest increase supports the thick crust hypothesis. If a thick insulating layer covers much of the nucleus, increased solar heating at the surface doesn't necessarily translate to much more sublimation from the deeper ice below. Different regions of the nucleus might have different properties. Some areas might have thinner crusts, making them more active. Others might be covered in thick, refractory material, making them nearly inactive. The total gas production is the sum of all these regions, weighted by their area and orientation relative to the sun. The rotation of the nucleus distributes this heating. As the nucleus spins, different regions face the sun, creating a day-night cycle. Areas in sunlight heat up and outgas. Areas in shadow cool down and become quiescent. If the rotation period is hours, then the heating cycle is rapid. If it's days, the cycle is slower, allowing more time for heat to penetrate before rotation carries the region into shadow. Unfortunately, determining the rotation period of 3-IATLAS from Earth proved challenging. The methods typically used involve looking for periodic variations in brightness as different regions rotate into view, but 3ATLAS's brightness variations were small and noisy, making period determination uncertain. Future observations with better signal-to-noise might resolve this. Alternatively, if spacecraft ever visit an interstellar object, they could determine the rotation directly through imaging and tracking of surface features. Such a mission remains a distant dream, but not an impossible one. The concept of an interstellar object intercept mission has been studied. The challenges are significant. First, you need to detect the object far enough in advance to plan and launch a mission. Second, you need sufficient velocity to catch up with an object moving at tens of kilometers per second relative to the sun. Third, you need to survive the encounter, either matching velocity for a rendezvous or conducting a high-speed flyby. For 3IATLAS, calculations showed that the optimal launch date would have been July 2024, a full year before discovery. Obviously, this wasn't possible. The spacecraft would have needed a velocity change, or delta V, of about 30 kilometers per second to intercept. This is enormous, far beyond what conventional chemical rockets can achieve. Nuclear propulsion might make such missions feasible. A nuclear thermal rocket, where a reactor heats propellant to very high temperatures, could potentially achieve the necessary performance. Nuclear electric propulsion, using a reactor to generate electricity for ion engines, could also work given sufficient time for acceleration. Another approach is solar sails, using radiation pressure from sunlight for propulsion. A solar sail accelerates slowly but continuously as long as it's exposed to sunlight. Given enough time, substantial velocities can be achieved without expending any propellant. For an interstellar intercept, the sail would need to be very large and very lightweight. These concepts remain largely theoretical. No spacecraft has been built specifically for interstellar object intercept, but as we detect more such objects, and as the scientific value of direct exploration becomes clearer, pressure will build to actually attempt a mission. The scientific return from such a mission would be extraordinary. Imaging the nucleus surface at high resolution would reveal its geology, craters from impacts, fissures from thermal stress, differences in color and texture showing compositional variations. Spectrometers could map the surface composition in detail. Mass spectrometers could analyze the gas composition directly without having to observe from afar. Sample return would be even better. Bringing back even tiny fragments of an interstellar object would allow laboratory analysis with instruments far more sophisticated than anything that can be flown on a spacecraft. Isotopic ratios could be measured with extreme precision. Organic molecules could be identified and characterized. The age of the material could be determined through radiometric dating. Such a mission would cost billions and take years or decades to execute, but consider what we've spent exploring Mars, a planet in our own solar system. Is a sample from another stellar system worth a comparable investment? Many scientists would argue yes. For now, we work with remote sensing. We collect photons from these visitors and extract every bit of information they contain. The photons traveled millions of kilometers, escaping from the comet's coma, traveling through interplanetary space, passing through Earth's atmosphere, and finally striking our detectors. Each photon is a tiny messenger carrying information encoded in its wavelength and polarization. The polarization of light from 3IATLAS provided unexpected insights. Polarization describes the orientation of the electromagnetic oscillations in a light wave. Unpolarized light has oscillations in all directions, perpendicular to the direction of travel. Polarized light has oscillations preferentially in one direction. When sunlight scatters off dust particles, it becomes partially polarized. The degree and direction of polarization depend on the scattering angle, the size of the dust particles, and their composition. By measuring polarization at different angles, astronomers can infer properties of the dust. The polarization signature of 3IATLAS was unlike any other comet. The extremely deep negative polarization branch suggests that the dust particles have unusual properties. Perhaps they're larger or smaller than typical cometary dust. Perhaps they have unusual shapes or compositions. Perhaps they're aggregates with specific structures. This finding adds another layer to the puzzle. Not only is the gas composition unusual, but the dust is also peculiar. This suggests that whatever made 3IATLAS different affects both the ices and the solids, pointing to formation conditions that differ systematically from the norm. The comparison with trans-Neptunian objects and centaurs is intriguing. These are bodies in the outer solar system, beyond Neptune's orbit or in the region between Jupiter and Neptune. They formed in the cold outer regions of the solar system and have been modified relatively little by solar heating. If 3IATLAS's properties resemble these objects, it suggests formation in a similarly cold environment. The parent stellar system might have had a massive outer disk extending far from the star, where cold temperatures allowed unusual compositions to persist. Or perhaps the system was simply colder overall, with the frost line closer to the star than in our system. The frost line is the distance from a star where water ice can survive in direct sunlight. Inside the frost line, water remains vapor or liquid. Outside, it condenses to ice. For our Sun, the frost line is at roughly 3 to 5 astronomical units in the asteroid belt. Different volatile substances have different frost lines. Carbon dioxide is farther out, carbon monoxide's farther still. If 3IATLAS formed in a region where carbon dioxide ice was stable, but water ice was partially depleted, perhaps near the CO2 frost line, it might naturally have high CO2 content. The exact conditions depend on the star's luminosity, the disk's density, and the dynamics of material transport within the disk. These details matter because they affect planet formation. The distribution of volatiles in a protoplanetary disk influences where and how planets form. Gas giants typically form beyond the water frost line, where ice greatly increases the amount of solid material available to build planetary cores. Rocky planets form inside the frost line, where only refractory materials condense. Earth's water likely came from beyond the frost line, delivered by comets and asteroids that formed in colder regions and later migrated inward or were scattered inward by gravitational interactions. The chemistry of Earth's oceans might carry fingerprints of these deliveries, isotopic signatures that reveal their origins. If Earth received material from interstellar objects, and statistically it must have over billions of years, then some of our water and organic molecules might have originated in other stellar systems. The atoms in your body, formed in ancient stars, might have journeyed through multiple stellar systems before ending up here. This is the grand picture of cosmic recycling. Matter is created in stars, dispersed by stellar winds and supernovae, incorporated into new stars and planets, ejected as comets and asteroids, wandering through interstellar space, captured or scattered by other systems, eventually destroyed in stellar collisions or planetary impacts. The atoms cycle endlessly, never created or destroyed, only rearranged. 3IATLAS is part of this cycle. Its atoms were created billions of years ago in stars that no longer exist. They were incorporated into a molecular cloud, which collapsed to form a star and disk. The disk material coalesced into planets and smaller bodies. One of those smaller bodies was ejected, becoming 3IATLAS. It wandered through the galaxy and now passes through our system, briefly visible before continuing its journey. Where will those atoms be in another 4.6 billion years? Perhaps scattered across interstellar space if the comet disintegrates from radiation damage, perhaps incorporated into another star system if the object passes close enough to be captured, perhaps still wandering, a frozen archive of ancient chemistry. The timescales involved are difficult to truly grasp. 4.6 billion years is longer than the entire history of complex life on Earth. Multicellular life arose less than a billion years ago. Humans have existed for perhaps 300,000 years, agriculture for 10,000, industrial civilization for 200. From our perspective, 4.6 billion years might as well be eternity. Yet from the perspective of the galaxy, it's ordinary. The Milky Way is about 13 billion years old. Many stars are older than our Sun. The oldest known star in our galaxy is approaching 14 billion years, nearly as old as the universe itself. These ancient stars have witnessed cosmic history we can only infer. 3I Atlas formed when the universe was about 9 billion years old, when the Milky Way was already well established. By that time, multiple generations of stars had lived and died, enriching the interstellar medium with heavy elements. The solar system would not form for another 200 million years or so. During those 200 million years, 3I Atlas was already wandering through the galaxy. It was there before Earth existed, before the Sun existed. If it survives long enough, it will still be there long after our star has died. This temporal span is humbling. The processes that govern the galaxy operate on these vast timescales. Stars form, live, and die over millions to billions of years. Spiral arms rotate over hundreds of millions of years. The galaxy as a whole evolves over billions of years. Our human timescale is so brief as to be almost meaningless in this context. Yet here we are, briefly conscious, capable of understanding something of these processes, able to detect and study objects like 3I Atlas. We exist for a moment, cosmically speaking, but during that moment, we can reach out with our minds and instruments to touch eternity. The tools we've built to study the universe represent accumulated knowledge and technology developed over centuries. The mathematics of orbital mechanics comes from Newton and his predecessors. The physics of light and spectroscopy comes from Maxwell, Planck, Bohr, and countless others. The engineering of telescopes and detectors represents contributions from thousands of opticians, engineers, and technicians. When we observe 3I Atlas, we're using this accumulated wisdom. Every observation stands on foundations built by previous generations. Every new discovery adds to foundations future generations will use. Science is cumulative, each generation building on what came before. This continuity across generations is itself remarkable. Individual humans are temporary, but human knowledge persists and grows. The astronomers studying 3I Atlas will eventually die, but their papers will remain, their data will be archived, and their insights will inform future research. In this way, they achieve a limited form of immortality. The data from 3I Atlas will be preserved in archives maintained by space agencies and observatories. Anyone with appropriate access can download the raw data and perform their own analysis. This openness ensures that discoveries can be verified and that new insights can emerge even years after the observations were taken. Sometimes, old data reveals new phenomena when reanalyzed with new techniques or new understanding. Observations of Halley's Comet from its 1910 apparition have been reanalyzed multiple times as our understanding of cometary physics improved. The same will likely be true of 3I Atlas observations. As the comet continued its outbound journey past perihelion, observers tracked how its properties changed. Was the activity decreasing symmetrically with distance, or were there asymmetries showing that the inbound and outbound behaviors differed? Asymmetries would suggest surface changes caused by the perihelion passage, such as depletion of surface ice or formation of new vents. Some comets show dramatic outbursts after perihelion, sudden brightenings as buried, volatile pockets are exposed. These outbursts can increase brightness by factors of 10 or more, though they're typically brief, lasting days to weeks. Whether 3I Atlas would show such behavior was unknown, but observers were watching carefully. The gradual fading as the comet receded would eventually make observation impossible even for the largest telescopes. The last detection would likely come from one of the giant telescopes in Hawaii or Chile, pushing their detection limits to capture one final spectrum or image. Then 3I Atlas would vanish from our view, still there, but too faint to see. After that last observation, the comet would exist only in memory and in data archives, but the scientific work would continue. Papers would be published for years. analyzing different aspects of the observations, proposing new models, comparing 3IATLAS to other comets and to theoretical predictions. Conferences would feature presentations about 3IATLAS. Graduate students would write theses analyzing its properties. The object would become a benchmark, a comparison point for future interstellar visitors, just as researchers still reference Oumuamua and 2I Borisov. They will reference 3IATLAS for decades to come. The nomenclature will evolve as well. Currently, interstellar objects are numbered sequentially, 1I, 2I, 3I. But as detections become more common, this system might require modification. Will there be a 4I, 5I, 10I, 50I? At what point does the numbering become unwieldy? Perhaps future naming schemes will include more information, such as the year of discovery or rough orbital parameters. Perhaps interstellar objects will be named after their discoverers more consistently. These decisions will be made by the International Astronomical Union, which governs astronomical nomenclature. Whatever the naming convention, each object will have a story, each will provide unique information, and each will remind us that the solar system is not isolated, that we're part of a dynamic galaxy where material constantly moves between stellar systems. As you lie here, relaxing into sleep, consider that the journey of 3IATLAS continues. Right now, at this moment, it's moving outward past the orbit of Mars, headed toward Jupiter, cooling as it distances itself from the Sun. The outgassing is slowing, the coma shrinking, the tail fading. In silence and darkness, indifferent to human attention, it continues. Months from now, it will pass Jupiter at a distance of several astronomical units. The giant planet's gravity will bend its trajectory slightly, adding a final gravitational nudge to its journey out of the solar system. This perturbation will change its velocity by perhaps a few meters per second, negligible compared to its overall motion, but enough to slightly alter its future path through the galaxy. Years from now, it will cross the orbit of Neptune, entering the realm of the distant ice giants. The Sun will be just another bright star, no longer the dominant object in the sky. The temperature will drop to just a few dozen degrees above absolute zero. All activity will have ceased. The last molecules of gas sublimated and dispersed. Decades from now, it will reach the scattered disk, the region where long-period comets originate in our solar system. Objects here orbit at distances of 50 to 100 astronomical units or more, taking centuries to orbit once, but 3IATLAS won't orbit. It will pass through and keep going. A century from now, it will be hundreds of astronomical units away, far beyond anything we can detect with current technology. If humans are still around, if civilization persists, perhaps we'll have better telescopes by then, capable of tracking objects at such distances. But more likely, 3IATLAS will have vanished completely from human knowledge, existing only as an entry in databases and archives. 1,000 years from now, it will have traveled about 3 light weeks, still well within what we think of as the solar system's sphere of influence, but utterly inaccessible to observation. The gravitational influence of the Sun will still be perceptible, but barely. The object is effectively back in interstellar space, and then the journey continues, through the vast emptiness between stars, through dust clouds and past distant suns, slowly orbiting the galactic center in company with hundreds of billions of stars and trillions of smaller objects. Perhaps hundreds of millions of years hence, it will pass through another stellar system and be detected by other observers who will wonder, as we do, where it came from and what it can teach them. This is the long view, the cosmic perspective that astronomy provides. Our individual lives are brief, but the universe continues. The processes we observe will continue long after we're gone. The atoms we're made of will continue, recycled through stars and planets and living things, endlessly transforming but never destroyed. 3IATLAS is a reminder of these truths. It connects us to the deep history of the galaxy, to processes that operated long before we existed and will continue long after. It shows us that we're part of something vast and ancient, that our small planet orbits an ordinary star in an ordinary galaxy full of wonders we're only beginning to comprehend. Let's drift a bit further into the story, into the details that connect 3IATLAS to the broader tapestry of cosmic history. There's comfort in these details, in understanding how the pieces fit together, how each observation reveals something about the universe we inhabit. The detection of interstellar objects represents just one small window into the larger phenomenon of mass transport through the galaxy. Every day, tons of material cross the boundaries between stellar systems. Most of it is microscopic, dust grains smaller than the width of a human hair, traveling at velocities that would vaporize anything in their path. These dust grains are everywhere in interstellar space. The regions between stars aren't truly empty. They contain about 1 atom per cubic centimeter on average, along with trace amounts of dust. That might sound like nothing, and compared to Earth's atmosphere with its 10 to the power of 19 molecules per cubic centimeter, it essentially is nothing, but accumulated over the vast volumes of space, it amounts to considerable mass. When our solar system moves through these dust clouds, the particles enter our domain. Most are swept up by the outer planets or drift in orbits that never bring them close to Earth, but some do reach us. Every day, approximately 100 tons of interstellar dust settles onto Earth's atmosphere. Most burns up as meteors, the shooting stars that people wish upon. A tiny fraction survives to reach the surface. Scientists can sometimes identify these interstellar particles. They have distinctive compositions, isotopic ratios that don't match anything formed in our solar system. The ratio of oxygen-16 to oxygen-18, for instance, varies depending on where and when material formed. By measuring these ratios in microscopic particles collected from Antarctic ice or the stratosphere, researchers can identify which ones came from beyond. These particles are ancient beyond comprehension. Some formed in the atmospheres of red giant stars that exploded as supernovae billions of years ago. The shock waves from those explosions compressed and heated gas clouds, triggering new star formation. The particles, tiny witnesses to stellar death and rebirth, were ejected into interstellar space where they wandered until chance brought them here. 3IATLAS is essentially a much larger version of these dust grains. Instead of microscopic, it's kilometers across. Instead of being pushed by starlight, it follows gravitational paths, but fundamentally, it's the same phenomenon. Matter from one stellar system entering another, carrying information about conditions elsewhere in the galaxy. The galaxy itself can be thought of as a giant recycling system. Matter doesn't stay put. Stars form from gas clouds, live their lives, then return their processed material to space. Planetary systems form, evolve, scatter their debris, and eventually die when their stars expire. The scattered material mixes with the interstellar medium, eventually being incorporated into new star systems. This cycle has been operating for billions of years. The atoms in 3IATLAS have likely been through multiple cycles. They were created in ancient stars, perhaps first-generation stars that formed when the universe was young. Those stars lived and died, releasing their material. The atoms drifted through space, were incorporated into later generation stars, perhaps multiple times. Eventually, they ended up in the molecular cloud that formed 3IATLAS's parent star and its planetary system. The disk around that young star contained processed material from many previous stellar generations, a mixture of compositions reflecting the diverse chemical history of that particular region of the galaxy. When 3IATLAS formed, it locked in that chemical signature. The isotopic ratios, the molecular abundances, the dust grain properties all reflect conditions in that ancient disk. By studying these properties, we're reading a message written 4.6 billion years ago in a place thousands of light years from here. The message isn't written in words, of course. It's written in chemistry. The ratio of deuterium to hydrogen tells us about temperature during formation. The carbon-12 to carbon-13 ratio reveals something about the stellar population that created the carbon. The presence or absence of certain complex molecules indicates what chemical reactions occurred in the parent disk. Each measurement adds a word to the message. Each spectrum reveals another sentence. Slowly, painstakingly, we reconstruct what that distant stellar system was like billions of years ago. We learn whether its star was similar to our sun or different. We infer whether its planetary system was similar to ours or alien in composition. The differences matter because they tell us about the diversity of planetary systems. We've now discovered thousands of exoplanets orbiting other stars. We've seen hot Jupiters, super-Earths, mini-Neptunes, and configurations completely unlike our solar system. We've learned that our system isn't universal, that planets form in many different architectures. But exoplanet observations tell us only about the planets themselves, not about the small bodies, the comets and asteroids that surely exist in those systems. Interstellar objects provide that missing information. They're samples from the asteroid belts and comet clouds of other stars, available for detailed study. If we could collect many such samples, we could begin to characterize how small body populations vary between stellar systems. Do all stars produce comet populations with similar chemistry, or does it vary systematically with the star's mass, age, or metallicity? These questions can't be answered with 3 examples, but they become tractable with dozens or hundreds. The Vera C. Rubin Observatory will provide those examples. Starting in the late 2020s, it will systematically survey the sky, detecting moving objects that would have been missed by earlier surveys. Its sensitivity and coverage will revolutionize the field, transforming interstellar object studies from a novelty to a statistical science. The observatory itself is a marvel of engineering. Located on Cerro Pachon in Chile, at an altitude of 2,682 meters, it houses a telescope with an 8.4-meter primary mirror and the largest digital camera ever built for astronomy. The camera contains 3.2 billion pixels arranged on 189 separate CCD sensors. Each image captures an area of sky equal to 40 full moons. Every few nights, the entire visible sky will be imaged. The data rate is staggering, about 20 terabytes per night, or 15 petabytes over the planned 10-year survey. Processing this data requires supercomputers and sophisticated algorithms that can identify moving objects, classify them, and flag anything unusual for human review. The system will generate millions of alerts per night. Most will be known asteroids or ordinary solar system objects, but hidden among them will be the unusual cases. Objects on hyperbolic trajectories, comets showing unexpected behavior, perhaps even something genuinely unprecedented. When the Rubin Observatory detects its first interstellar object, and then its second, and then its 10th, we'll begin to see patterns. We'll learn about the size distribution, confirming or refuting the statistical puzzle that 3ATLAS presents. We'll measure the rate of different compositions, learning whether high CO2 objects are rare anomalies or common variations. We'll also learn about the history of these objects. Some will be young, recently ejected from their parent systems, moving in relatively straight lines through the galaxy. Others will be ancient wanderers like 3IATLAS, their paths bent by countless gravitational encounters, their surfaces modified by billions of years of radiation exposure. The ancient objects are particularly interesting because they're time capsules from an earlier epoch of the galaxy. 3IATLAS formed when the Milky Way was younger, when the metallicity was slightly lower, when the rate of star formation was different. It carries information about that era, preserved in its composition and structure. Over cosmic time, the composition of the interstellar medium has changed. Early in the galaxy's history, there were fewer heavy elements because only 1 or 2 stellar generations had lived and died. As time passed, more supernovae occurred, enriching the gas with metals. Stars and planets forming later have higher metallicity than those forming earlier. Our sun has intermediate metallicity. consistent with formation about 4.6 billion years ago. 3 IATLAS, forming around the same time, should have similar metallicity. Future interstellar objects might have different metallicities, telling us about their ages and the history of their birth systems. The study of these chemical fingerprints connects astronomy with archaeology. We're excavating the past, not by digging into Earth, but by examining objects that have survived from earlier epochs. Each interstellar visitor is an artifact, telling us something about conditions that existed long ago in distant places. This perspective transforms how we think about these objects. They're not just interesting curiosities or scientific targets, they're historical documents, primary sources for understanding galactic evolution. Every measurement we make adds to our understanding of how the Milky Way came to be what it is today. The galaxy itself has a history, a story of formation and evolution spanning 13 billion years. It began as a diffuse cloud of primordial hydrogen and helium, perhaps mixed with smaller protogalaxies that merged together. As the cloud collapsed under its own gravity, stars began forming, first in chaotic bursts, later in the more organized spiral structure we see today. Those early stars were different from the Sun. They contained almost no heavy elements because none had been created yet. When they exploded as supernovae, they seeded space with the first carbon, oxygen, silicon, iron, all the elements that make up rocky planets and ultimately living things. Each subsequent stellar generation inherited the heavy elements created by previous generations. The metallicity increased gradually over billions of years. By the time the solar system formed, enough heavy elements existed to build terrestrial planets. By the time life arose on Earth, the elements necessary for biology were abundant. 3 IATLAS participated in this history. Its atoms were forged in multiple stellar furnaces, ejected by supernovae, mixed into molecular clouds, incorporated into a protoplanetary disk. The carbon in its organic compounds, the oxygen in its ice, the silicon in its dust, all have individual histories stretching back billions of years. These atoms are older than the comet itself. The atoms existed before the comet formed, before the solar system formed, before the Milky Way had its current structure. Some might be nearly as old as the universe, created in the first stellar generations. Others might be younger, created more recently in massive stars that lived and died quickly. There's something profound in this realization. The atoms that make up everything we see, including ourselves, have histories. They've been through cycles of creation and destruction. They've existed in different forms, as gas in nebulae, as part of stars, as components of planets, as dust in comets, as molecules in living cells. The particular collection of atoms that currently makes up your body will not remain together. Eventually, they'll be released back into the environment, scattered, incorporated into other things. In the very long term, on timescales of billions of years, they might be ejected from Earth, wander through space, perhaps end up in another stellar system entirely. This is the ultimate recycling. Matter is never destroyed, only transformed. The cycle continues indefinitely. As long as the universe exists, every atom has an infinite future ahead of it, an endless series of transformations we can't predict but can be certain will occur. 3 IATLAS, from this perspective, is just passing through another phase of its existence. The atoms that make it up have been many things before and will be many things after. For now, they're arranged as a comet, following a gravitational path through our stellar system. Later, they'll be something else. Perhaps, in the far future, long after the sun has died and the Earth is gone, some of those atoms will be incorporated into a new planet around a young star. Perhaps conscious beings on that planet will look up at their sky and detect interstellar visitors just as we do. Perhaps some of those visitors will contain atoms that are currently part of Earth, ejected by the solar system's demise, wandering through the galaxy for billions of years before being captured elsewhere. This circular nature of cosmic history is comforting in a strange way. Nothing is permanent, but nothing is lost. Everything transforms, but everything continues. The universe is a closed loop, matter cycling through different forms, energy flowing from order to disorder but never disappearing. Entropy increases, yes. The universe trends toward equilibrium, toward heat death, toward a state where no further changes can occur. But that end state is trillions of years away, so distant that it's essentially infinite from our perspective. For any time scale we can meaningfully contemplate, the universe remains dynamic, full of change and process. 3IATLAS represents one tiny process in this vast dynamic system, a few trillion kilograms of matter arranged as ice and rock following a trajectory determined by ancient gravitational interactions. It's almost nothing in the grand scheme. The galaxy contains a billion trillion times more mass, yet here we are, paying attention to this one small object because we can, because it tells us something we want to know. Human consciousness is perhaps the universe's way of knowing itself. We're collections of atoms arranged in patterns that allow self-awareness and understanding. We can contemplate our origins, wonder about our place in the cosmos, and study objects like 3IATLAS to learn about the processes that created us. This capacity for wonder and understanding is remarkable. Most matter exists without awareness. Rocks don't know they're rocks. Stars don't ponder their fusion reactions. But here on Earth, and perhaps elsewhere in the universe, matter has arranged itself in patterns complex enough to look back at the cosmos and ask questions. Those questions drive the study of interstellar objects. Why do they exist? Where do they come from? What can they tell us about the galaxy? These aren't practical questions in the sense of improving daily life. Nobody's survival depends on understanding 3ATLAS, yet we study it anyway because the questions themselves matter to us. This is what it means to be human, in part. We're curious beyond necessity. We want to understand things even when that understanding has no immediate practical value. We build telescopes and train specialists and spend billions of dollars to look at distant objects simply because we want to know. And what we learn becomes part of our shared knowledge, part of the heritage passed to future generations. Children today can learn about interstellar objects in ways that were impossible a decade ago. Children in future decades will have even more information thanks to missions and observations happening now. This accumulation of knowledge across generations is one of humanity's greatest achievements. Each generation builds on what came before, pushing the boundaries of understanding slightly farther. The astronomers studying 3IATLAS stand on the shoulders of Newton, Galileo, Kepler, and countless others who established the foundations of celestial mechanics and observational astronomy. Future astronomers will stand on the shoulders of today's researchers, using the methods and insights developed now to study objects we haven't detected yet. The progression continues as long as civilization persists, as long as we maintain the infrastructure and culture that supports scientific inquiry. That infrastructure is fragile. It depends on stable societies, adequate funding, public support for basic research, and training new generations of scientists. None of these are guaranteed. Throughout history, civilizations have risen and fallen, taking their accumulated knowledge with them into decline. But for now, the infrastructure exists. Telescopes scan the sky nightly. Researchers analyze data and write papers. Students learn the methods and prepare to carry the work forward. And occasionally, an object like 3IATLAS appears, reminding us why we maintain this whole enterprise. The reminder is this: we're part of something larger. Our solar system is connected to the galaxy through these wandering objects. The galaxy is connected to the universe through the physical laws that govern everything. We're not isolated, not separate, but deeply embedded in cosmic processes that operated long before we existed and will continue long after. There's humility in this realization, but also a strange kind of empowerment. We're tiny and temporary, yes, but we're also capable of understanding vast systems, of recognizing our place within them, of asking questions that span billions of years and trillions of kilometers. 3IATLAS, now receding from the inner solar system, doesn't know we're watching. It has no awareness of its significance, no understanding that its passage through our system has generated conferences and papers and late-night observations, and this very narration designed to lull you to sleep with cosmic facts. It simply moves, following the path laid out by gravity, indifferent to observation. And yet, through our observation, it becomes meaningful. It becomes part of human knowledge and culture. It becomes a point of connection between humanity and the broader cosmos. This is what we do with the universe. We observe it, measure it, try to understand it, and in doing so, we give it meaning that it wouldn't otherwise have. The universe exists without us, certainly, but the universe understood, contemplated, wondered about, exists only in minds like ours. So as you drift into sleep, consider that you're part of this process. By listening to these facts, by thinking about 3IATLAS, by letting your mind wander through the implications, you're participating in the human endeavor to understand our cosmic context. You're connecting your brief consciousness to processes and timescales far beyond individual human life. This connection is valuable. It provides perspective on our everyday concerns. Problems that seem overwhelming shrink slightly when viewed against cosmic time. Worries that keep you awake seem less urgent when you consider that 3IATLAS has been traveling for 4.6 billion years, that it will continue traveling for billions more, that the universe is patient and vast beyond comprehension. Not that your concerns don't matter, they do, to you and to those around you. But there's value in occasionally stepping back, in taking the cosmic view, in remembering that we're part of something much larger than our immediate circumstances. The visitor came and will go, and life continues. Your life, with its joys and challenges, its routines and disruptions, its small triumphs and setbacks. But now you know that while you live your life, above you, beyond reach but not beyond understanding, objects from other star systems pass through our neighborhood, carrying information about distant times and places. Let that knowledge settle into your thoughts as you settle into sleep. The universe is stranger and more wonderful than any fiction. The facts about 3IATLAS, every one of them true, everyone based on actual observations, everyone representing real processes that actually occurred and are occurring. Sleep now, knowing that the cosmos continues its ancient dance. Stars form and die. Planets orbit, comets wander between stellar systems, and here on Earth, briefly conscious, we watch and wonder and slowly, incrementally understand. The visitor that appeared in July 2025 will be remembered as a milestone in our growing catalog of interstellar objects. Future historians of science will note it as the third confirmed, the one with unusual chemistry, the one that sparked debate about size distributions and technological hypotheses. But for now, it's simply here, moving through our space, visible to our telescopes, available for study. The opportunity is temporary, but the knowledge gained will persist, adding to the foundation of human understanding about the galaxy we inhabit. Rest well, traveler through space and time. The universe is vast, but here you are, briefly conscious within it, capable of contemplating objects from other stellar systems, capable of understanding processes that span billions of years. Good night. May your dreams be as deep as space and as peaceful as the cold dark between the stars, where objects like 3IATLAS wander silently, patiently, carrying their ancient messages across the galaxy, waiting for someone, somewhere, to read what they have to say.